There are a number of interesting things in Idaho that are not fully understood yet. The Western Idaho Shear Zone is a large structure that we are still working on trying to understand what exactly happened.
We're also studying areas like the Sawtooths, where we know that the range is bounded by faults, but not as much about where the pluton extends underground. A pluton is a granitic rock which forms when magma is hardened in the earth and then over time is exposed.
What we're hoping to get out of this project is to help kind of resolve some of these mysteries about the landscape here in Idaho.
The data set we are collecting is gravity data. Different rock masses have different densities, and more dense objects have a stronger gravitational pull. And so as we go along our traverse measuring the gravity, we'll be able to determine certain rock types beneath our feet.
This transect was set up by other researchers in the IDOR project who placed seismometers in the ground at regular intervals to gather data about the structure of rocks beneath the surface along this line.
This is actually a study in geophysics, and so it has to do with the laws of physics when they're applied to geology. This one uses mass, which is a physics concept, to determine the thickness of the crust or the composition of rocks by taking that physical measurement.
So what we're doing is we're taking this gravity transect and we're combining it with other geophysical methods like seismic data, and each geophysical method has a different weakness, and so by combining them you can eliminate those weaknesses.
Each morning before we start our transect, we set up a GPS base station and a gravity base station.
The GPS base station is a unit that we will leave there the entire day, and it will be collecting data and making sure that the satellites are getting an exact location there. And the reason we set that up is that the other GPS stations that we use throughout the day will actually be taking their position in relation to that GPS. So that at the end of the day, we can go and shut that one off, and that will have an exact point, and we'll have our points based off of that.
The machine we use to take gravity readings is called a gravity meter or gravimeter.
The base stations that we set up for the gravimeters are mainly to correct for drift later in the day over the course of the measurements.
If you measure at the beginning and the end of the day, you can make a correction for the gravity meter drift.
The gravimeters need to be as close to level as possible because we want to know exactly what gravity is or how much is being pulled directly downward, not at any other angle offsetting it from the center of the earth.
Inside each gravimeter, there's a mass, which is a stainless steel weight on a really sensitive spring. In fact, it's only one in several thousand springs made by the manufacturer that is perfect enough to be used in a gravimeter. The gravity directly below the gravimeter pulls down on the mass, and that changes the position of the spring, which you can see when you look through the eyepiece. To take a gravity reading, you adjust the dial until the spring is centered on a specific point, which is the 2.7 reading line for this specific gravimeter. The dial numbers are your measurement, which you convert to gravitational force by using a conversion table. Because the spring is so sensitive, it needs to be locked in place while you're adjusting the dial. Otherwise, you might bounce the spring and have to wait for it to settle down before you can take another reading, which will take quite a while. After the base station is set up, we move to our first station to take a reading. We use field books to record both the GPS and gravity reading at each location. The person taking the gravity measurement will read it off to the other person in the group who sets up the GPS unit.
3426.71.
That person writes down the number and repeats it back to the person taking the reading, who also writes in their book. It's kind of a double check to make sure we're collecting good data. Later on, when we're putting the data into an Excel spreadsheet so it can be analyzed, we'll have both people go back through it with their field books just to make sure all the data is exactly the same. We take a reading every half kilometer, about 3 per mile. Depending on the weather, we can usually collect about 20 gravity measurements a day. At the end of the project, we'll have gravity data for more than 1,000 points along the transect.
Gravity depends on so many different factors, how far you are from the center of the Earth, the density of the rock around you, the topography, such as the mountains in the background, are actually influencing our readings this far away. They're pulling just slightly because they're so large. On the other side over here, we have a slight ravine, and that lack of Earth is affecting the measurement too. So when you bring that all together, it can help us with the other techniques try to figure out if there's something very dense pulling down, or we get a strong surface layer or defined boundary from the seismic data. We know that there's definitely some sort of structure there in the subsurface that's causing that.